National Design Contest 2012-2013. We are team number 16, 5 from Digital Technological University, Delhi. This is our topic, that is ultra low power and cost effective wireless instrumentation and telemetry support system for solar mobility applications. Myself, Rohit Gupta, and this is my friend Jaspreet. Basically, we are going to demonstrate our own prototype of a ultra low power cost effective wireless instrumentation and telemetry support system for solar mobility application. Now, what is this solar mobility application? As these days cost of fuel is increasing as well as the pollution in the environment is increasing, so solar mobility applications are basically those vehicles which run on the power harnessed from the sun. We both are part of a solar car team in our college, so we have been making these cars for about 2 years now, and this is the module we developed for this solar car of ours. All the operating parameters are very critical. The power is coming from the array, it is being stored in the battery, and the battery is being used to run the motor. So everything should be in equilibrium. Now, to manage this equilibrium, we need to know where is the equilibrium. So, using this telemetry support system, we guide the driver about the equilibrium point and help him achieve the optimal equilibrium point.
The main idea of the project was to create an interface which will allow us to use multiple nodes, shown here as node A, node B, and node N, wirelessly to a central station, and enable the data acquisition and control of various control units on these nodes via PC GUI. The GUI for this purpose was created using Visual C#. First, this is the component that we use in this project. We have used MSP430G2552 IN20 microcontroller and MSP430G2452 IN20 another microcontroller for LCD interfacing, and MSP430G2231 also for LCD interfacing on node B. And LM25 temperature sensor, a Darlington transistor array ULN280C, EZ430 RF2500 target board, TS750 MO5C 5V regulator, L2950 3.3V regulator, and TPS713QB 3.3V very low dropout regulator. And also the software that we use for this project are Code Composer Studio version 5.1 from Texas Instruments, IR Workbench, Visual Studio 2010 for creating the PC GUI, and CAD Software for creating our schematic of PCB. And now we'll proceed with our demonstration of the project.
So what we have here is a unit that we made during the initial stages of the contest for testing and evaluation purposes. The final unit that we made for the contest will be discussed later by Rohit. Now let us focus on this one. So what we have here is MSP430G2452 microcontroller for LCD interfacing, MSP430G2553 IN20 microcontroller for which is linked to this EZ430 target board via UART interface. We also have some voltage regulator in this circuit. This is ALM7806 voltage regulator, and this is TL750 MO5C a 5V voltage regulator. Also this one is TPS7133 QP 3.3V very low dropout regulator. Also since this was made for just testing purposes, so we have 4 input channels here and 4 control channels here. This can be extended up to 12 channels, and on the we also have some onboard sensors here. On channel 1 we have a HI300 Hall sensor, and on channel 2 we have LDR, and on channel 3 we have a LM35 temperature sensor. So now we will proceed with the demonstration. So the square wave input to this EZ430 target board is provided by this Control Easy MSP430 graphic user interface that we developed for controlling GPIO pins on this MSP430 launchpad. Now as you can see, we have turned node B on as well. So I am now going to connect node A and node B to my laptop, and we will see how the system actually works. Also note that these two nodes have been connected to my the PC wirelessly using this EZ430 target board along with the debugger module. So now I am going to select my COM port, COM51 connect. So these two, the system has now been connected. Now I'm going to turn channel 1 and channel 2 on, and I will assign these to node 1 only, node 1 or node A. So the value on the channel 1 input is currently 3, which is basically the input voltage to this Hall sensor. Now we'll bring the opposite pole of this magnet to this Hall sensor and we will see how the value changes. So as you can see, the value is now dropped to somewhere around 0 volts, and again it jumped up to 3 volts. Also the channel 2 on this node A is connected to this LDR, and now we will reduce the intensity of the light falling on this LDR and see how the value change. So as you can see, the value is now on channel 2 is now reduced again, so it is increased again. So as you can see, the channel 1 is linked to control panel 1 and channel 2 is linked to control panel 2. So I am going to select some multiply constants first, and we will see how the control units actually work. Say I have selected a multiply constant of 16.5 on channel 1. I am going to assign it to node 1 again, and a multiply constant of 19.8 on channel 2, and again I am going to assign it to node 1 only. So as you can see, the values has been multiplied by the multiply constant that I have set, and this value is indicated by these analog meters as well. So basically on these control panels we have 3 modes of control. Mode 1 is basically switching the actuated control unit on and off by these buttons. Mode 2 and mode 3 are basically selecting the cutoff. Suppose we want to create a system in which we are reading a temperature value, and above some temperature cutoff we need to switch some unit on, say a cooling fan or some other related unit. So we can select a cutoff from these modes. So let us first select some cutoffs. Say I am going to select 10. Also let us say we are going to control port 1 control channel from port 1 input channel only. So from N1 to N1. Now I am going to select mode 2. In mode 2, if the input value falls below this cutoff value, the actuated control channel will be turned on. So I am going to bring the other pole of this magnet to the Hall sensor again, and we will see what happens. So as you can see, the activation signal has been sent because this value, that is 0.194, is obviously less than the cutoff value 10, and this LED, as you can see, is turned on. So I have now reset the entire system, and we will see one more example. So I am going to connect these two nodes, node A and B, to my laptop again, and I am going to turn the channel 1 and 2 on. And this time as well I will assign these channels to node 1 only, and I am going to select a scaling factor of say 15.43 on channel 1 and assign to node 1, channel 2 assigned to node 1. So in the previous example we saw how we can control a control channel on the same node by the input value obtained on that node only. This time we will control this node 2 with the input value that we obtain from this Hall sensor of the node 1. Basically we will see how we can link multiple nodes in the system using the GUI only. So I am going to select node 2 here, and say first of all let us select some cutoff value. Say I am selected 13 this time, and mode 2 again. So I am going to bring the opposite pole of this magnet to my Hall sensor, and we will see what happens. So as you can see, the value is now reduced, and an activation signal has been sent by the control panel 1 to this control panel 2, and we can see this LED is now on, which indicates that the control signal has been generated. So this is how we can control multiple nodes in a system using the same GUI, and as you can see, it is very easy. All you have to do is select the appropriate constants and appropriate nodes. You have to select the node from which you want to obtain your signal, and node to which you want to send your control signal, and that's all you have to do. So this was the main purpose of creating this whole system, that it should be easy for the user to select the parameters and finally make this thing work. So now Rohit will demonstrate the system that we finally made. Basically, we converted this whole system into a booster pack, and now Rohit will explain how that unit actually works. Thank you.
The board that we showed you earlier was developed only for demonstration purposes, so because it's a bit neater to show it on that perf board. But for the actual use in the car, we made booster packs that can be fitted onto the launch pad, and this provides us a very compact means of telemetry. As you can see, we have a RF module plug-in over here where we connect the EZ430 module. It has on-board voltage regulators for 12 volt, 5 volt, 3.3 volt and ground. So we can connect a variety of sensors. There is also a Darlington which is being soldered as an SMD component on the bottom side. This is used to select the loads that we want to switch. Like in a car we have headlights, fans for cooling systems. So for that purpose we use the Darlington. It has a 500 milliamps per channel. 2 channels can be clubbed to get a higher current rating sometimes. This fits onto this completely. There it goes. This is the TransReceiver booster pack. We also made a sensor booster pack which can be fitted onto this, so that all the sensor needs are met in. There is a 5 volt connector to drive the LCD on it, which comes from the parent board. Goes like this. So here we have the complete module. The LCD fits over here, and voila, we have the complete board. You can see it is very compact. It can be placed anywhere in the car. This is a PCB made out of FR1 material.